All right, welcome my friends. In this video, I'm going to be going through Machine Learning section 2.8, which is titled Unsupervised Learning. In this notebook, we're going to be exploring the iris dataset, which is the same dataset we looked at in the PowerPoints related to flower measurements. And we're going to be performing principal component analysis to reduce the dimensionality of this dataset, as well as k-means clustering in order to discover clusters within this dataset. As is always the case, I recommend that you go to File and save a copy in Drive of this notebook so that you can fill out the code as you're watching along with this video. I've already connected to my Google Drive here, and I've already loaded in the dataset. You may need to go to your folder, go to Drive, My Drive, and find the location where you have this dataset. I have it here in Datasets, and you may need to go and copy the file path so that you can run this code and get that dataset in here. Now I've already kind of just filled out some of the first couple of answers here because these are pretty repetitive based on some things we do in basically every data set. Let's just view the first few rows of iris using head. It's called iris DF. And we can see similar kind of result here to the PowerPoint. We have the sepal length, the sepal width, the petal length, and the petal width, as well as the species. And we are going to actually, when we do the k-means clustering, we're going to kind of do it without the species because we don't really want to give that away, and see if the clusters kind of match up with the actual species that we have here. We can also see the shape of this data set. It is 155 rows. We can see that there are no null values, and we do have quantitative variables. They're floating point for each of those variables, which is great. And the species is an object for categorical variable. We can see from the quantitative variables kind of the range of the possible values here. Looks like petal width is kind of the smallest on average, whereas maybe the sepal length is looking like the biggest one typically, and the other ones are kind of in between here. If we run the value counts here on the species, we can see we have completely perfectly equal classes with 50 of each of those types of flowers. Okay, I've kept a little bit more of the code in here. I promise we will get to coding some of this stuff on our own. Basically, what this is doing here is it's just kind of fixing this a little bit. I don't really like the titles as they are here. I'm just going to put them into slightly more compact titles that are lowercase with an underscore. So this is just renaming some of the columns. And then also you'll notice in the species column that we have this kind of iris dash at the beginning of each one. And I'm just running some code to replace that, to get rid of the iris dash and replace that with a blank. And the resulting data frame is going to look like this. So now we have these slightly nicer titles for each of those columns. And now the species only has the species rather than the iris prefix on it as well. All right, let's go ahead and examine some of the relationships between the features here. And we can most easily do that with a heat map. And the heat map is going to show us the correlations between all of our different variables that we have here. So I'll go down here and kind of look at this. We've done this before, I believe, in a couple of other videos. But the way I'm going to do this is I'm going to put in the feature columns first, and I'm just going to put these into a list, which are the ones that we want to make this heat map out of. And that's going to be these four. I'm just going to copy and paste those in here. And I'm going to put quotations around each one and commas between them. There we go. Now we have our feature columns in a list here. Looks like we want to set the figure size to 7.5. So the 7 is kind of like the width, and the 5 is kind of the height. So we can do that by doing plot.figure, fig size equals 7.5. And ideally, you would probably not always know what the right figure size is, and sometimes the default might be okay, but I've already kind of pre-done this and found that 7.5 is a pretty good size for this heat map. And then it's been a bit since we've done the heat map, but this comes from Seaborn. That's why I'm importing Seaborn here. So we do need the SNS kind of prefix here. And then we're going to want to do the heat map. And you may remember, it's been a while since we've done this, but for a heat map, usually the first thing you put in here is a correlation matrix. And I think previously we may have just kind of created the matrix first. But for sake of minimizing the code here, and since we don't really need that separate step, we can just kind of create the correlation matrix within here. So the way that we do that is we would put in the data frame that we want to create the correlation matrix from. We put in the columns that we want the matrix to be created from, which are what we just created here. And then it's just dot core for the correlation matrix, right? And there's a couple other things we can put in here just to kind of spruce it up a little bit. Usually these look a little nicer if we put in annotation equals true, because that will display the exact correlations rather than just colors. The colors give you an idea of the correlations, but it's nice to have the actual numbers also with them. And then this format I can put in to round the values, and that will be maybe 2 decimals. Okay, and then I could also put a title on here. So plt.title can say correlations between iris measurements. And let's see if we got that. And there we go. We get a nice little kind of heat map going here. So the correlation matrix on its own, just this thing right here. If I was to run this, it should give me the same kind of results, but just in like a table form, right? But this heat map function is going to allow us to get this nicer output with it. So I'm not going to keep that one. I'm going to keep this one. The annotation equals true ensures that the numbers still show up in here. And now I have this kind of color scale. The whiter it is, the closer to 1, and the blacker it is, closer to, I guess, negative 0.4 is the lowest that it gets here. I think I could change this to make it a negative 1 to 1 scale, but it looks like the lowest that we got was about negative 4. And I'm going to be looking for some stronger correlations here. So I can see sepal length. Obviously, the main diagonal is correlations with itself. So sepal length with sepal length is, of course, going to be 1. Sepal width is going to be 1. But so that one's not quite as interesting, but the other values are more interesting. So sepal length is not very highly correlated with sepal width. It's not very much, only negative 0.11. 0.87 with sepal length and petal length. That's a pretty high correlation, so that means those two tend to go together quite a bit. Same thing with sepal length and petal width. And in general, if I just kind of go throughout here, I see a lot of a little bit higher correlations. I see some 0.96s here. I see some negative correlations that are not particularly strong, but still some amount of correlation there as well. So basically what this correlation matrix is showing us here, or this heat map is showing us, is that we do have a fair amount of correlations between our data. And that usually means that principal component analysis is going to be a good thing to maybe apply to our data, right? Because principal component analysis is going to create uncorrelated features that still contain a lot of the information within these. And if these variables have a lot of correlations with each other, then maybe we can kind of reduce it down to only 1 or 2 variables rather than 4, and still capture a lot of the same information. So that's the reason why having this correlation matrix or heat map is kind of helpful or important. It tells us that PCA might do a pretty good job at kind of condensing this data set. Okay, so let's go ahead and separate our features on our labels. I'm going to set x equal to just the features of our data frame, which is iris_df with those feature columns. Now, it's not like this isn't a supervised machine learning algorithm, so we don't have like the features and then a target. It's not really like that, but I mean, kind of in a way, we're kind of almost treating this a bit like a supervised learning task eventually when we get to the clustering, because we do have the species that are kind of in there, and we kind of want to know if we applied k-means clustering, how well would that actually do at kind of figuring out those species. So we're kind of cheating a little bit here by actually having a labeled data set that we're gonna still use an unsupervised learning task on, but I'm kind of getting ahead of myself a little bit here. So we do want to have our features in X, which will just be those four columns that we have in feature columns, and then I'll separate the species as well. And then we can just take a look at X, and we can see that we've got those four variables just by themselves without the species column along with it. Okay, so we are going to want to standardize the features for principal component analysis. Remember, the reason for this is we want to make sure that the different variables don't play like a kind of a larger role here. And so it's usually recommended for PCA to standardize the features. So we will use the standard scaler here to create z-scores for all of these values. So we've done this many times before. So maybe for sake of time here, I'm just going to copy in the answers. We just create a scalar object by calling the standard scalar. We're going to want to create a copy of x so that we don't change the original one. We don't want to lose the original values, but we want to create this scaled version. At this point, we will not have scaled the values. To actually scale them, we have to apply this fit transform method from scalar. So we can say the feature columns from x scaled should now be scaled. They're the scaled version of X feature columns. Now, when I was looking at this the first time and I was kind of experimenting with this, you might kind of think that, okay, wait just a minute, doesn't X scaled only have those feature columns in the first place? And the answer is yes, right? X, which is also going to be our X scaled, all it has is those feature columns. So you might be thinking, well, why do I have to specify feature columns? Well, this actually ensures that the result we get of this is also a data frame. If we didn't do this, it actually wouldn't store it as a data frame, which is going to be problematic for us. So this might seem kind of like a little repetitive here, because you're like, X scaled already has the features. But this ensures that the output's also a data frame. So, all right, so running this, maybe we'll see the head here as well. Maybe rounded to 2 decimals. That's what I did here. So now we have those 4 variables again, but they have been appropriately scaled based on the z-scores. Now, okay, I was going to say a second, why did I get the same number 5 times in a row? And it looks like we had some repetitiveness in here. This looks like maybe it was sorted in some way. Maybe it was sorted by petal width or something from the beginning. So we end up getting some of the similar values, but I bet you if I did like a 15, maybe we will. Oh, I did round, not round. 15 needs to go here. And I am seeing, now I'm seeing different numbers. Let's run this again. Round to 2 decimals. There we go. That's what we need. Yeah, and I am seeing some different values here. Maybe it's not completely sorted, but it does look like we got a lot of negative numbers early on. So maybe there's some sort of sorting going on in this data, because we should have kind of like equal number of negatives and positives. But we can tell at this point that we have properly scaled our data. Okay, so now we can get to the good stuff. We can actually go and apply principal component analysis. So just like with a lot of other machine learning algorithms in scikit-learn, we kind of create an object first that is then going to have some methods that we can apply to do different things. So we're going to create a PCA object, and then that PCA object is going to be applied to our data in order to create the principal components, right? So first we need to create a PCA object, and I'm going to call this PCA all to represent that this is going to be a principal component analysis variable that contains all 4 principal components. Later we're going to just focus on like 2 of those components, but this what we're going to create is going to contain all 4 principal components. So let's create that. And then this one also has a fit transform method. So we can say I'm going to call this xPCA_all is equal to PCA_all dots. So PCA_all is this object I created, dot fit underscore transform. And I want to transform that scaled data I just created. Next, I want to create a list of component names, PC1 through PC4, because I'm going to create a data frame. So kind of the disadvantage here of this PCA is it doesn't actually automatically output a data frame, but I do want the result to be in a data frame. So the easiest way to kind of do this is create a list first here of the component names, which are simply just going to be, I'm just going to call them PC1, PC2, PC3, and PC4. Let me actually just show you right now why this is necessary. Like if I just output this, you'll see this is not a data frame. It does contain the principal component information, but it's not really displayed in a way that we want it to. It's like in a NumPy array. So we don't really want this in this form. So I'm going to create a data frame out of that. So I'm going to say PCA all data frame is equal to pandas.dataframe. And the way I'm going to create the data frame here is one way to create a data frame. There's kind of like multiple ways you can use this pd.dataframe. In many cases, we've put in like a dictionary where the columns, like we would do the dictionary, and we have like the column name, column one, and then we'd have the values maybe in a list. That's one way we've used this pd.dataframe. But you can also put in you can first put in the columns, which I'm gonna, or I guess actually first put in the rows and then put in the columns. So I can put in the rows of this data frame, which are going to be what we just had, um, these values, right? And then you put in the columns, which are the component names. And these don't need to be in a dictionary now. And if I do it that way, then I should be able to see the head of this. And it looks like I wanted to round this maybe to 2 decimals. I do have to specify columns here. That's what I'm missing, I think. There we go. Awesome. So now I have my principal components. So I have principal component 1, 2, 3, and 4. So just a reminder of what this has done here is it has, we started with 4 features, right? The 4 different kind of lengths based on the flowers. And now we've created these principal components where each one has a decrease, explains a decreasing amount of variance. So the most important one is PC1, which you could say kind of contains the most information about our original data, right? And PC1 and PC2 together are going to do PC2 is going to be like the second most important, and then PC3 is going to be the third most important, and then PC4 is going to be the least important. And you can kind of see that in the numbers here. And once again, I think the data set was sorted to some degree, so we see a lot of more negative values here, first of all, but you see that the PC4 is a lot more centered towards 0, and some of the other values have a little bit more kind of variation going on. Maybe we'll do like 20 rows. What if I just don't even do the head? And then I get to see the end ones. Yeah, there is some sort of sorting kind of going on here. So I do see a lot larger values later on. But the point is that I see like less variation in the later PCs. And the earlier PCs, I see more variation. And therefore, they're more important. They're kind of capturing more of the information of that initial data set. So let's kind of examine that in a bit more detail here. So this PCA all that we created here has a number of methods associated with it. So we use the fit transform in order to transform our scaled data. And we saved that into PCA all and then created this data frame out of it. But there are a couple of other ones we could do. It does also, once you've done that fit transform, you can output the explain variance as well as the explain variance ratio. And I'm going to go ahead and create a data frame kind of around that. And I'm also going to do the cumulative sum to get like a cumulative amount. So I want to know, what percentage of the variance does just PC1 do? And then not just PC2, but PC1 and 2 together. And that's what this cumulative sum is going to allow me to do. And this one's a little bit involved, so I'm just going to copy this one in for sake of time here. And I'll try to explain it. So I'm going to create a data frame, and I am going to use the dictionary kind of method to do this. And the first column of the data frame is going to be titled principal component, and it's going to have those component names, which are PC1 through 4, right? That's going to be our first column. Our second column is going to be the component variance, which is the method. We use this method explain variance. It's going to give us that explain variance. If we want it as a percent, we can take the explain variance ratio and multiply it by 100. And then also, if we want the cumulative sum, we can take the explain variance ratio, and then we can do the cumulative sum on that times 100. And that's going to give us the cumulative amount. So I think this will make more sense if we output this. So now you can see here, I think we had a similar output in the video. We have each principal component, the amount of component variance. Remember the variance, those add up to 4 because there's 4 principal components. The original data set also had a combined variance of 4 because they were scaled. When they were scaled, they each had a variance of 1 since we were using z-scores. So these also add to 4, but now they're kind of a little bit more lopsided, right? PC1 is 2.93. And PC2 is 0.93, and they kind of decrease as you go on. And the percentage of explained variance is right here. The first one does 72.77%, so that's 2.93 divided by 4. The second one is 23.03%, and then they start to decrease. And then we have the cumulative amounts here, right? So the 95.8% is kind of these two numbers added together, or the 99.48 is the first three added together. Okay, we can go ahead and plot this. So I'm going to do a bar chart for this, and I'm just going to paste this in here. So I'm going to do matplotlib bar chart, and I'm going to use those component names as the we can go ahead and just display this. The component names are going to be on the horizontal axis here, and then we have the explain ratio values times 100 for the vertical axis, and maybe we should do some axes here. Let's do the let's put in some axes information. So we'll use principal component as our x-axis label, variance explained percent as our y label, and a title of explain variance by principal component. And I'll add a little grid to it as well to make it look a little nicer. And there we go. We got our 4 principal components, and we have the variance explained. So this just kind of displays the same kind of information that we had here. It's these numbers, but just displayed a little bit nicer so we can more easily compare across those 4. So we can see PC4 is very unimportant compared to like PC1 or 2. Okay, so we're going to go ahead and just keep the first 2 principal components because we can see that the first 2 together encapsulate 95.8% of the variance. So let's just stick with those 2. And that's going to allow us to create some visualizations and just look at those 2 and not have to focus on all 4 at once. So I'm going to create a new data frame called PC all data frame. Or actually, no, I already have that data frame. That data frame already exists, right? That's what I created up here. Somewhere I created that. Yeah, I created that right here. So that's this data frame, but now I'm going to add on. I'm going to add on the species label. So we could say species is equal to species. So that species, I think we defined that somewhere much earlier, way at the beginning. We defined that somewhere. Where was that? I know somewhere early on we did that. Right here. We defined that already. So that already contained the species information, and now we're going to tag that on to our principal component information. So now we can see that PC all. We can see that now we have the principal components as well as the species info. All right, so let's go ahead and visualize the first 2 principal components. Looks like I'm going to do the figure size of 8.6 again, or I'm not sure if that's the same number I had before. And I'm going to use Seaborn here. Seaborn works better when you have it actually in a data frame. Matplotlib, maybe if you don't have it in a data frame, you may want to use that. But here I have this data in a data frame. And what I'm doing here is I'm going to plot the 2 principal components. And just for fun here, I'm going to add on the species as a color. So let's go ahead and let's see here. Notice a small error there. This says penguin species displayed. It should say iris. Right? The penguin one will be the practice one. So I'm going to go ahead and add a title here. I'm going to add some grid lines with a little bit of a fade with that alpha. And then we can just do plt.show to show that nicely. And we can see here that we've got the 3 species of the flowers. We have the Setosa, which are over here. We have the Virginica, which is over here in green, and we have the versicolor that is over here. So we can already see, we already kind of have the answers here with the species. We can see once we graph the 2 principal components that they do separate very nicely when we plot these. Now we're going to, in a minute here, we're going to try to see if we can determine these clusters using k-means clustering, assuming we didn't know the species, and try to see what those are, because that's kind of a more traditional workflow. You might just have some data and you want to figure out what clusters you can kind of place them into. But here we can see based on the species information we already have that there are these kind of groups that we have here, right? All right. One other thing we can do here is we can examine the component loadings. This just shows us a little bit more about how those principal components were created. We don't really need to have this, but this is just something nice to have. Um, I'm not gonna. I'll let you look through this code a little more detail if you want to, but I'm just gonna go through this and just show this. So it shows us for PC1 and PC2 exactly what those component loadings are, and those are mathematically used to create each principal component. And I would direct you again to the video for the exact calculation. It's kind of like a weighted average based on these values and the observations in your data set to get the principal components. So this is kind of a key step along the way there. All right, we made it to k-means clustering. Let's go ahead here and we're going to now see if we can create some clusters in here using k-means clustering without telling it what the species are, and then we can actually compare with the species and see if it was accurate or not. So let's see if we can run k-means clustering. We'll use a k of 3 because we already know there's 3 species. And let's see if it can get us to be relatively close to what the actual species are here. So that's going to be the focus of the rest of this year. So just like with any other machine learning algorithm in scikit-learn, we're going to have to kind of basically create an object. In this case, it's called we'll call this k-means model, and then we have to use this k-means. And we have a lot of options for things that we can put in here. So of course, we're going to have to tell it how many clusters we want to use. And this is sometimes one of the harder things to determine for k-means clustering. Later, we will kind of try out a couple of other values of k. But for right now, I'm going to use n clusters equals 3. To make this reproducible, I'm going to set a random state of 42. And there's another actual nice kind of hyperparameter we can use here, which is n underscore init. And one of the disadvantages we discussed when we talked about k-means clustering was that sometimes you can have you have those initial clusters or those initial centroids, which are just kind of randomly assigned. And sometimes the initial random assignment of those can make it so the clusters are maybe not as good as they could be once you've run the algorithm. So what this is going to do is it's going to create, it's going to try to do it however many times you ask it to. So I could say init is 10 to start 10 different 10 different initial random starting points. And then it's going to kind of say, okay, which of those 10 created the lowest inertia? Remember, the inertia is kind of our measurement for how well it's doing when we have the lower inertia, which is it's kind of like summing the squared distances from each point to the centroid. So it's gonna choose which of those 10 or 100 or whatever you put in here end up getting the lowest inertia. So I'm going to use n initial equals 10. Okay, so we have a method here called fit predict. That's what it's called here. It's not fit transform. It's called fit predict. So we can create cluster labels is what we're going to create, which are going to be we're going to have labels basically 0, 1, and 2. Since we're creating 3 clusters, it's going to label each observation in our data set as either a 0, a 1, or a 2. Those are going to eventually correspond to the 3 species of flowers that we have, but right now it has no idea that there are even any species of flowers. We're not going to tell it any of that information. We're just going to see if it can get those here. So let's create those cluster labels. So we have to call our model here, and we got to call this fit predict, and we got to put in the scaled information or the scaled data. So now we already had that PCA data frame before that has the species column as well as the principal components. But let's add on this cluster. And now let's go ahead and display that. I need a capital M here. There we go. Okay. So now we can see that we have the principal components, we have the actual species, and we have the cluster associated with the species, right? And it's looking like good news here because it looks like we had a cluster of one for the first 5, and that also was kind of the species that was going on here, right? Now, I just still kind of emphasize this a little bit more that typically with a clustering task, you wouldn't be using it in this way. It might be a case where you're just trying to learn about your data and see, if you can put it into clusters. But since we kind of have something that can kind of be verified as a cluster, it's kind of nice to be able to look at that and kind of see if our algorithm's doing kind of well on something that it might not really know about. See if we can match those clusters up with the species. Okay, so as I mentioned, the cluster labels are going to be just basically arbitrary 0, 1, or 2. It doesn't really know what species it's associated with, but we are going to be able to kind of match that up here. Now, it does give us the inertia. So if we wanted to, we could output the inertia. So we kind of call our model dot inertia underscore, and that's going to give us the inertia. Remember, the inertia is the sum of the squared distances from each observation to the centroid. So in k-means clustering, we have a centroid. So there'd be 3 different centroids, which are kind of at the center of each of the clusters. And if we square all the distances from each observation to the centroid, we get about 141-ish. So let's go ahead and visualize the clusters here. I'm just gonna copy some code in here. It's just another seaborn scatter plot referring to that data frame. I'm going to use PC1 and PC2. In this case, I'm going to use the hue of cluster. So last time I think I used the hue of the species, but now I'm going to use the hue of the cluster. And let's just put in some title info here. And let's run this. And now we can see the k-means clusters displayed using PCA. So we have the PC1 and PC2, and we have the clusters. And if we will go up a little bit, we can see these are the actual amounts, right? We have the species here, and we can see there was some kind of overlap here, right? So our clustering was not, maybe I should have displayed them side by side, but I'll just grab a screenshot of this so we can kind of see it together here. But I can see that it did different color schemes, but that's all right. But I can see that here when we did the clustering, it doesn't really have any overlap, right? There is some overlap here between those, so that's going to be a little bit harder for the k-means to be able to identify, which is fine. I mean, the goal here is not generally to actually do a classification, but this is just an observation we can make based on what was actually there. So that is our graphed cluster information. And now let's do the comparison. So we can do this comparison using this crosstab function. And this crosstab function is going to basically, or method is going to basically give us a table that is going to count how many, it's going to be somewhat similar to a confusion matrix here, but it's going to give us the species on the, let's see, what do I do here? The rows, I think I'm going to do the species, and then on the columns, I'm going to do the clusters to see where we have something matched up and where something where we might have some errors. So I'm going to put this in here. So I'm going to call this cluster comparison, and we're going to call this crosstab method here. And the first 2 inputs here are really all that I need, and that's going to give me the, I'm going to put the species of my data frame on the rows, and I'm going to put the cluster information on the columns. And what it's going to do is it's going to count kind of the matchups and where they don't match up, right? So is it the case that, every time that we have a versicolor, it's a 1, or every time that we have a virginica, it's a 0, right? Or is there a lot of differences, right? And then just for sake of clarity here, I'm just going to label the row names with the species values and the column names with the cluster numbers. So let's go ahead and display this. So this is going to be a table. So we can see that it did extremely well with setosa. So every single setosa was labeled as a 1. That's great. Versicolor, not quite as good, still decent. So it labeled 39 of the versicolors as 0, but 11 of them were 2s. And for Virginica, it labeled 14 as 0s and 36 as 2s. So we can see that it did an okay job at placing those in those clusters that we knew kind of already existed. Okay, so let's go ahead and calculate a few different values of inertia, and then we're going to make an elbow plot to see what different values of k, what the inertia would look like, and that's usually how you would determine the appropriate value of k. So I'm going to do this. I'm going to use a range function to generate the numbers from 1 to 10. And those are going to be the different values of k I'm going to test and see what the inertia is going to be for. So I'm going to create a blank list here for the inertia values. and then I'm gonna run a for loop here to populate the inertia values. So I'm gonna say for k in k values, which is this range here. I guess I could have just done the range here, but I'm just gonna do it here. Now for each one of these, I'm gonna have to create a new model. So I'm gonna say, okay, for each time, I'm gonna create a model. And in that model, I'm gonna say I want to have the number of clusters. I want to have k clusters, and I'm gonna use a random state of 42, and I'm gonna do 10 initial starting points and choose the best one. And then for each one, I'm gonna fit the model on the scale data. And then I'm going to take that inertia values list that we have there, and I'm going to append to that list the inertia. Okay. And let's just see how that did. Let me just print that out. Inertia, spelled that wrong. Inertia values. Oops. Just hit a cell. I didn't mean to do that. Okay, there we go. So it did give us the inertia values. Looks like it's 600 when k is 1, and then 223 when it's 2, and then it seems to go down. It's always going to go down. But the point of analyzing these is trying to find when it starts to not really go down very much anymore, right? And to figure that out, probably the elbow plot is the easiest thing we can do. So I'm going to use, since I don't have a data frame here, I'm going to want to use matplotlib. So I'm going to use matplotlib's plot. I'm going to plot the k values and the inertia values together. So the k values are the 1 through 10s, and then the inertia values are these numbers together. And to easily be able to see these, I think the default does not give me x ticks from 1 to 10. So right now, yeah, it just gives me like 2, 4, 6, 8. But I want to have the X tick marks be 1 through 10 so I can easily see those. And I'll also add some axes label information. Okay, so I've got a number of clusters from 1 through 10, and I have the inertia values, and we would want to choose the k where once we start increasing k, we're not really seeing much of a decrease in the inertia, and that probably happens at 3. When I go from 3 to 4, there is a decrease, but not really too much, and that kind of makes sense because we do know that there are 3 different types of flowers. So we probably would choose an inertia, or sorry, a k of 3 here. All right, that finishes this video, and under 40 minutes, so that's okay. I know this is going to be a little longer one due to kind of the 2 topics here in unsupervised learning. So hopefully you're able to follow along with this, and we're doing okay. These are the only 2 unsupervised learning algorithms I think I'm planning to cover in this class or this in this lecture, or overall in this class. But there are definitely a lot of other unsupervised learning algorithms. A lot of them do some of the same things as these 2 do, but just in a little bit of a different way. So I would encourage you, if you have some time and you're interested, to maybe research some of those other algorithms as well. But that's all I had to talk about in this lecture, so I will see you sometime in the next one.